Hi, welcome to Intro to Forecasting 4. Today's episode is going to be about what to do if you don't have much information to go on, and how to make good estimates anyway. So, what do you do if there's no reference class? The first thing to ask is, are you sure there isn't? Like, really? Because when it comes down to it, often there's something that can serve as a decent proxy for a reference class. Maybe you have to adjust it a bit. Maybe you have to look at two different classes and kind of average them. The point is, before you go too far into the rest of this video, it's important to just take a moment and say, actually, is there something I could use as a reference class, even if it's not super obvious at first? Let's assume, however, you've decided the answer to that question genuinely is no. The solution is to make a Fermi estimate. So how does Fermi estimation work? Essentially, there are 3 steps. You take your question that's quite hard to estimate an answer to, and you split it up into smaller questions, or questions that it's easier to answer. Then, for each of those smaller questions, you either estimate the answer, or you do the same process again and split those questions into smaller questions. You start off with something that's quite difficult. You split it into some questions that are a bit easier. You split those into some questions that are a bit easier again. What you can end up with is a set of estimates that aren't terribly hard to make, that when combined will give you an estimate of something that's really quite difficult. This is best illustrated with an example. I'm using a piece of software here called Guesstimate, which I intend to walk through in a lot more detail in a separate video. For now, just think of it like a notepad tool. That's all I'm using it for today. I'm not really exploring the full functionality. So I've decided to pick sort of a classic Fermi question. It's the sort of thing you might get in a physics interview if your interviewer was feeling a bit weird. So it's like, estimate the sort of surface area of leaves on a sort of mature oak tree. And it's like a classic example of a Fermi question because it's not a fact someone would know, but it's something that people can rely on their everyday experiences for and sort of break down in quite a straightforward way. So that's what I'm going to do. So the first thing I'm going to do is I'm just going to think, well, what would it be useful to know? Well, if I knew the number of leaves, that would be useful. So let's create a variable for that. If I knew the number of leaves on this oak tree and the sort of surface area of one leaf, that would help. Okay, so let's start with that. Can I break these down further? I think the surface area of one leaf I can estimate kind of without any sub steps. I can think of maybe a 10 centimeter by 10 centimeter square is about a leaf. So that's going to be 200 square centimeters because you have to count both sides of it. So I'm just going to write that in. Okay, so now number of leaves on an oak tree, this feels like it should be broken down a bit further. So we're going to use our recursive process. Let's just get our final answer here. So this is going to be total area. And I'm going to use, so I'm just writing equals, and I can click on these cells. So that one times this one. And press enter, and at the moment there's an error message being thrown up because we don't have the number of leaves. So what do we need to find the number of leaves? There's a few approaches here. The one I'm going to go for is I'm going to kind of imagine the tree as a big sphere, or just the leafy bit as a big sphere, and then I'm going to kind of try and guess the density of leaves in a particular bit of that sphere. So I can I feel like I can imagine kind of about this much oak tree, so I can kind of imagine counting the leaves in there. Let's see how this goes. So let's go for radius of the leafy bit, and I'm going to say maybe 4 meters. I'm going to stop putting units on, which is lazy but acceptable. So then actually the volume of the leafy bit is going to be fine. So it's just equals 4/3 times pi times this cubed. Okay, so 270 cubic meters. Now, what else do we need? We now need the leaf density. So what I'll do here is I'll go for the volume of the amount of oak tree I can kind of imagine in front of me. So, and then the number of leaves in that box. And then I'll separately do leaf density. So by leaf density, I mean the number of leaves per unit volume in the leafy bit rather than the density of a leaf. So I'm imagining a box that's half a meter by half a meter by half a meter. And then the number of leaves, this is kind of hard, so I'm just going to have to I'm just visualizing a bit of tree in front of me. This isn't a great method, but we're going to go with it. I want to say 50, maybe you kind of got 10 leaves and you got kind of 5 layers because there's definitely closer space because you got different branches and stuff. Whatever. This is just an example. Let's assume I can count 50 imaginary leaves. So the number of leaves per unit volume is then going to be that divided by that. So then the number of leaves is going to be the volume of leafy bit times the leaf density. So that times that. One thing I like about Guesstimate here is you can kind of see which things are piling in where. So what's that giving me? That's giving me like 21 million square centimeters for the like total area of leaves on an oak tree. Like, I don't know what the right answer is here. It's probably within an order of magnitude of that. I'll be bold and say, yeah, I reckon it's within an order of magnitude. So like about 10 to the 7th, the nearest order of magnitude. But like, I don't really know, and that's fine because this is just an example. So that's kind of how to break down a problem. Let's quickly kind of recap what we did. So I said I want to know like the total area of all the leaves on this oak tree, and I thought, well, what two numbers would I like to know? The area of one leaf and how many leaves there are. The area of one leaf I could kind of like get a good guess for, so I just did that. And then the number of leaves there were, I thought I'm going to have to imagine something else because I can't just like guess that in one go. So I kind of said like, how big is the leafy bit of the tree, and then how many leaves are there per bit of the leafy bit of the tree. So that was this bit, and then how many leaves are there per leafy bit of the tree. I just kind of like imagined a section and looked at its volume and how many leaves there were in that section. So the point here is to get a number that really like, there's no way I'd have come up with 20 million as opposed to like 100 million or 1 million if I'd just been asked the number off the top of my head. Like I wouldn't have got, I wouldn't have known where to start. So like this, I didn't have any confidence in at all. But now having pulled some numbers basically out of thin air, I have like a better idea. This is probably a better guess than me just pulling one number out of thin air. Okay, so that's Fermi estimation in general. What I want to talk about now is how we can apply this to forecasting, because I think, for me at least, there's a slightly different algorithm I can think through. How I think about Fermi estimation as it comes to forecasting is as follows. First, consider like two possible worlds where the probability of the event occurring seems to be meaningfully different. Then, like, estimate the probability that the event occurs in those two different worlds. Then this again is a process we can then use recursively. So for each of those worlds, maybe there's something else that could cause this event to happen or not. Again, I'm going to illustrate this with an example. But the thing that's different here for me is rather than kind of like splitting the number that we care about up into some different things, instead I just want to split the idea itself. Okay, so for a second example, let's have a look at building a model for this question. This question currently on Metaculus. I'll link to it in the video description. And it's, will the Tokyo 2020 Olympics take place on schedule in 2021? That's a bit of a weird sounding question. Basically, because all of the branding was already made for the 2020 Olympics, they're still going to be called the 2020 Olympics, even though they've been rescheduled for a year later than originally planned. I think this is a question that like doesn't have an obvious base rate. For the original sort of Olympic cancellation, by that point there have been many other sort of big politically important events that had been cancelled by coronavirus. So there were things you could use for a reference class. We don't really, unless we go back to like post-Spanish flu, have a good reference class for like after a major international pandemic, do international events start happening again? So I think this is a case where it's defensible to say there isn't an obvious reference class, I have to use other factors. There are still some reference classes we can come up with, but I think it's good enough that you might want to use this sort of approach. So I actually don't intend to make any probability estimates here. I realize that might be a bit mean, but I really think the value in forecasting is like just learning to generate things yourself. What I do want to do, however, is break down what I meant when I said sort of split the question into different possible worlds, and then split those possible worlds into sub-questions, which is worth thinking about. So obviously the main thing that's impacting whether the Olympics takes place on time is like whether it's safe in some general sense of safe. And obviously safety for like, in a forecasting sense would need to be put much more specificity on that. But for the purposes of like breaking down a question, I don't think that's a terrible place to start. So let's just start with sort of two worlds. And in one of them, it is broadly safe to have like an international sporting event in July, and in the other, it broadly isn't. Like maybe that's just my personal assessment of whether or not it's safe. And then what we want to do is say, in those possible worlds, what's the chance of the Olympics taking place? And I think in the world where it is safe by like my estimate, given that I'm fairly conservative in my willingness to do things that endanger hundreds of thousands of lives, I think the chance of the Olympics going ahead on schedule is like almost 1. I think this is one of the rare cases where I will go without much thought above 95, and maybe I'll go for like 99 here. So let's just say happens given safe. So I actually decided I wasn't going to put too many numbers in. I'll put some numbers in when it's kind of obvious what's going on. A harder question actually is, what's the chance of the Olympics happening given that it's not safe? And I'd probably have to break that down further. First, though, let's have a look at what's the chance that the Olympics is safe and what's the chance the Olympics isn't safe. So for these, we'd kind of have to do the same thing. So maybe what we'd want to do is say is safe is like safe given vaccines on schedule, safe given vaccines not on schedule. So now what we need is like, what's the chance that vaccines are on schedule? And now just to kind of show you how all the numbers will connect up, I'm going to like put really just complete nonsense numbers in here just so we can see how Guesstimate will pull everything together. So maybe I think the chance that vaccines proceed on schedule is like 0.5 because I know nothing about vaccines. So maybe I think that the chance that everything's safe given that the vaccine rollout happens is 0.7. I want to emphasize here again, these aren't meant to be my actual estimates. These are just things that I think, are within 0.5 of the correct answer. Maybe safe given that vaccines are not on schedule. And I might, because I'm only doing this for myself here, I don't have to be too specific. By not on schedule, I mean like less than the current planned rollout. If I wanted to split this question further, probably vaccination is important, that we could kind of go broadly as is currently planned, worse than is currently planned because something's gone wrong, and like better than is currently planned because another vaccine got developed, or like the institutional problems that have stopped vaccine rollout being as fast as it should have been have somehow magically evaporated because people realized coronavirus is really bad. Whatever. Let's just pick 2 for now. So not on schedule. It's less likely to be safe. Maybe we go with like a 0.4. So now, is safe. What we want is, given that vaccines can either be on schedule or not, this is just the sum of these two. And clearly I've done something wrong here. It's not the sum of these two. It's the sum of these two multiplied by the vaccines on schedule. I am a math teacher, so that's embarrassing. But at least I checked my answer quickly and decided whether it's something sensible before moving on. It's 1 minus this, but I'll code it in properly. So 1 minus vaccines on schedule. There we go. So we've got like 55% chance of being safe, which means this is just 1 minus that, which is nice. 1 minus is safe. Great. Then if it happens, given that it's safe, we've got 0.99. If it happens, given it's not safe, let's say, well, there's a lot of political capital invested. Maybe let's go like with 30% chance it happens, even if it's not like broadly safe. So then what's the chance it happens? The chance it happens is the chance it happens when safe, which is happens given safe times probability of safe, plus the chance it happens when not safe, which is happens when not safe times probability of not safe. So we get a 67% chance that the Olympics will happen on schedule. In summary, there's not that much to this actually. Just like split up the possible futures into different worlds where there's meaningfully different chances of the event happening. If that's not enough to get a good forecast, do the process again for each of those different events, split those into different things, estimate those probabilities, and shove all the things back together using something like Guesstimate to do it. I'm going to put a separate video out of just me working through a bunch of Fermi estimates in Guesstimate because I think that could be useful, but I'm going to stop the video here and have that be a separate thing for people that are interested in watching it.